These notes will help you better understand inequalities. We're going to look at how to solve, graph, and set up inequalities from word problems. To start, we're going to get a little bit of a definition and vocab. Inequalities are very similar to equations, except instead of everything being equal, it's possible that they might be unbalanced, or one side could be larger than the other. There are 4 inequality symbols, and we're going to start by just making sure you have words to go with each symbol. So our first symbol is the greater than symbol. Second, we have the less than symbol. The third one is greater than or equal to. And our final one is less than or equal to. When you graph a solution to your inequality, you can use a number line to do that. And when you are using either of the greater than or less than, you're going to be using an open circle. So that just means you're going to have a circle with nothing filled in. If you're graphing either greater than or equal or less than or equal, that's when you're going to use a closed circle. So the number on your graph will have a circle, but it will also be filled in. One way that I remember which one to use is the open circle is not filled in and it does not have a line underneath it, whereas the closed circle is filled in and there's a line underneath your symbol, so it's like that one little extra marking reminds you that you're going to fill it in. That tells you that the solution you're graphing is included in the solution set, whereas if you're using an open circle, it's everything up until that point. So let's look at an example of what I mean by that. This example is x is greater than 2. This is going to use an open circle. So on my number line, I'm going to put a circle where the 2 is. And then if x is greater than 2, that means it could be anything bigger. It could be 3 or 5 or 2,482, anything to the right on my number line. And so to show that, I'm going to use array, and I'm basically going to show that it's all of those possible numbers. So anything that the ray hits could be a possible solution to that inequality, including all of my decimals and fractions that might be somewhere in between on that line. Okay, next example, this time I have 5 is greater than or equal to x. So if 5 is bigger than x, then that means that x has to be less than or equal to 5. I like to put my variable first. It just helps me read things correctly using the right name for the symbol, and it helps me graph it so that I know which way my ray should go. This time it's the less than or equal, so I'm going to be using a closed dot to graph this. So on 5, I'll put my circle and then I'm going to fill it in so that it's closed. That means 5 could be a solution to this inequality. And since x is less than 5, I'm going to draw my ray going to the left, and that shows that it can be anything that's smaller than 5. Again, fractions, decimals, in this case, any negative number you could think of would make this inequality true. Okay, now we're going to look at how to solve an inequality. Now that we know how to solve equations, inequalities are going to work the exact same way. So in my example, 3 plus 2x is greater than 11. I'm going to start by solving just like I normally would, and I'm going to cancel out my constant first, so I'm going to subtract 3 from each side. This is my 0 pair, so I'm left with 2x is greater than 8, and now I'm going to divide by 2 on each side. So my inequality becomes x is greater than 4. And now, just like the last two examples, I can sketch out a graph. This is the greater than symbol, so it's just going to be an open circle, and anything greater than 4 would be all of these numbers over here, 5, 6, 7, 8, anything to the right. So I'll draw my line with an arrow on the end to make it a ray, and that's going to be my final graph. Inequalities can be solved like equations in every way except for one small exception. With the exception, just to prove why it works, I'm going to start with a very simple inequality that says 5 is greater than 4. So we know that that is a true statement. So I'm just going to write true next to it. Okay, that's pretty simple. Now what I'm going to do is use a couple of my equation solving techniques, and I'm just going to multiply both sides by -1. Okay, we know that as long as we do the same thing on both sides, I'm allowed to do that. So -1 multiplied by 5 is -5. 4 multiplied by -1 is -4. So now if I bring down this inequality symbol, now I have a problem. -5 is not larger than -4. If you think about your number line with 0 right here, -1, -2, and -5 would be over here. Everything to the left is smaller, so since this is not true, we have a problem. First of all, I'm going to write false next to it. And now, in order to make this inequality true, I'm actually going to need to flip my inequality symbol. So -5 is less than -4. Now I have a true statement again. So that's going to bring us to one of our rules that we're always going to use. And that rule says that whenever we multiply or divide by a negative number, you will have to flip the inequality sign. Okay, and again, the reason for that is just to make sure that we're keeping it as a true statement. If we don't flip it, then it's not true anymore. All right, let's look at our example. Just like before, I'm going to solve it and begin by canceling out my 5 positives. So I'll get -3x is less than 9. And then I'm going to divide both sides by -3. So on the left side, I'll get positive x. On the right side, I'll get -3. And this is the part where we have to remember our rule. Okay, the number that I multiplied or divided by on both sides was a negative. And so I need to make sure that I flip my sign. Instead of less than, I'm going to use the greater than symbol. So my final answer, x, is greater than -3. And then we can graph it. This will be an open circle. And everything greater than x would be the numbers to the right. So we'll fill in our array to show that x is greater than -3. Okay, next we're going to look at another vocab, or rather 2 vocab words, and those words are discrete or continuous. These apply when you are looking at graphs of word problems where there's a context to go with what you're graphing. To start, discrete is going to represent any quantity that cannot be split into smaller pieces. So as an example, people or cars or t-shirts, those are things that don't really make sense to talk about having 2.5 people or 4.3 cars. It's not really going to make your word problem make very much sense in real life. When you are graphing something that is discrete, your graph will look a little bit different than the ones we've just done. Instead of using an array, you're going to use a set of points. So if I sketch out maybe the graph of x is greater than 1, we'll do greater than or equal to 1, and I number a few of these points. We'll include some negatives. Then I'm going to put a solid filled in dot at each of those points that represents an answer. So notice how this is a little bit different than using the array. We're just going to use the solid dots because I can't have 1.5 or 2.3 or 3 1/3. I can only have those whole numbers. So again, discrete can't be split into small pieces. It's something where your answer is represented only with specific numbers. Next, looking at continuous, this is going to represent quantities that can be split into smaller pieces. So an example of that, if you're talking about lengths or time. So in lengths, if you have 3 feet, you could split that into 1/2 of a foot, or that could be split into inches, where you could have 1/4 of an inch, and it could be broken down into smaller and smaller pieces. For a length, it would make sense to have fractions and decimals that represent it. Same thing with time. An hour could be split into minutes. Minutes could be split into seconds. Seconds could be split into milliseconds if you want to be especially precise. So those are the types of things that it would make sense to use array, and that would be just like what we were looking at before. So if I have x is greater than or equal to 1, then I'm going to have a solid dot at 1, and I'm going to use my array to show that it could be any of those fractions or decimals in between. Okay, so let's look at that with an actual word problem. You want to purchase a bicycle that costs $265. We'll put the $sign in here. It says, so far you have saved $128 and you plan to save an additional $20 per week. First, we're going to write and solve an inequality to find the number of weeks it will take to save at least $265. So just like when we were setting up our equations from word problems, when we were just doing regular equations, we're still going to define our variable. So it says find the number of weeks. So that's going to tell me what to use as the variable. So I'm going to write W equals number of weeks. And then it says that I am going to save $20 per week. So I would multiply 20 times my variable. And then I need to include the $128 that I've already saved up. So that would be an expression to represent how much money I have and how much money I'm planning to save each week. Then I'm going to compare that to the $265 that I need to save. Okay, our last piece is to determine which inequality symbol to use. If we are using the words at least, that means we could have exactly 265, so that could be an or equal, or it has to be more than. So the correct symbol for at least is always going to be greater than or equal to, because we can go above $265 and still have some left over, but we can't buy the bicycle until we have at least that much. All right, now we can go ahead and solve our inequality. So I will subtract $128 from each side. So I get 20W is greater than or equal to 137. Next, we need to divide by 20 on each side. And then we can do long division to figure that out. Add a decimal point with a 0. And then 20 goes into 178 times. And then we'll need one more 0. 20 goes into 100 5 times. So my exact precise answer is 6.85 weeks. But in the context of the problem, it doesn't really make sense to have 85 hundredths of a week, especially if I'm getting $20 per week. So this is a case where time wouldn't really make sense to be continuous, and instead it would be discrete. We're either going to have our money at 5 or 6 or 7 or 8 weeks, not at anything in between. So with my graph, I'm going to start numbering. Whenever you make a graph, you want to make sure you have at least 2 numbers on each side of the number you're graphing. So a total of 5 numbers at a minimum on your graph. Because we're talking about how much we need to save, it would really make more sense to say that W is greater than or equal to 7 weeks, because that's the first point where we're actually going to have enough money to save. And this is going to be a discrete function, and that means that I'm going to use a set of points. So possible solutions to my word problem, W can be 7 weeks, or 8 weeks, or 9 weeks, or 10 weeks, or anything larger than that. So this would be a graph for my final answer. All right, those are all of your examples for inequalities. Hopefully that helps, and good luck solving them.